Okay, today we're gonna focus on shortest path problem. So many decision problems you can see from emergency vehicle routing. And while you're driving, you use navigators from your home to your destination, such as NGCU main campus. So the navigator will give you shortest path or quickest path or cheapest path, depending on how you're set up on navigator. So the navigator will use GPS, and GPS will track of your vehicle location, so they make sure you're on the right route path. So this is a special case of transient problems. As I said, shortest path problem can be solved by several different algorithms, but we're going to use transient problem. Why we can use transient problem? Because we only assume there's one supply node with one supply node with a supply of 1. So that supply should be labeled by negative number. So we can say -1. And there is only one demand, which is a destination, like NGCU campus. So there's only one demand, U. And as we had a discussion, demand should be labeled by positive number. So only one demand will be labeled by +1. So now you have 1 - 1 from your home and +1 at the NGCU campus. So all other nodes have supply demand of 0. So 0 supply, 0 demand. So you only have one supply -1, only one demand +1. So we can use transient problem to solve this shortest path problem. So actually, I'm going to use example from the textbook. For example, if you drive from Birmingham, Alabama to Virginia Beach in Virginia, you may have many different routes, right? So many different routes. Routes are feasible paths. So, but we're gonna select only one path out of so many different routes. So let's find shortest path. Now I say shortest path, but actually these number represent travel time from node I to node J. So let's say the quickest path. First thing is we need to find the decision variables, right? So as we had discussed, each arc represent a decision variable. So the number of decision variables is actually the number of arcs in this graph. Actually, this graph is a simplified network. Because if you drive from Birmingham to node 3, actually you have there are so many different segments, and you never know what's going to be happen between 1 and 3. Maybe there is a construction, maybe snow and rain, and so it actually reduces your travel. And so it can be longer, or it can be shorter if you drive faster. So this number, let's assume these are the estimated travel time, the numbers. Estimated travel time. If you want to have a robust problem, you can use some kind of distribution for. But here we just assume this is average travel time, which is estimated. So we're going to find the quickest path. And the first thing is we need to find a decision variable. So let's say decision variables. First things, what is the decision variables? Right, from node 1 to 3, arc node 1 to 3. Let's say A13, A12, A23, A24, A35, A36. Now A46, A47, A69, A68, A78, A710, A911, A1011. These are the decision variables, right? So the second thing we need to define objective function. Okay, so for example, from 1 to 3, if you choose to travel through 1 to 3, then you cannot travel 1 to 2 because you only select either one. So now here we have one supply -1 and then one demand positive number and Bosnian range. So if you choose to drive from 1 to 3, A13, and travel time is 3 hours. Then if you choose travel from 1 to 2, and travel time is 2:45. So you can make a list of this using these decision variables. These are the very long. So let's just say that XAIJ times cost travel time. Let's use T. So through arc IJ and travel time IJ. But we need to summation of these all. So we're going to use and travel time TIJ. So J. You can make it simple. So if you have M number of J and N number of I, you can use M and N. So this is a simplified version of object function. So do you have any questions so far? So we're on the same page? Okay, thank you. Now, this object function is subject to supply constraint, demand constraint. All right, supply constraint. Let's take a look at this. If you start from node 1, you may go through node 3 or 2. You cannot go both, right? It means if you choose X13, right? So there's no inbound. There's no inbound traffic to node 1. So it's a 0, right? And no, before we're doing that, we need to make sure total number of supply will be equal to total number of demand, because it's -1 and +1, right? Because total supply equal to total demand. We use balance of flow rule, inflow minus outflow will be supply or demand. equal. So let's start from node 1. There is no inflow, so it's a minus. And there are two outflows, A13 minus A12 should be equal to -1. Are you getting this?
Yes.
Thank you. If you rewrite this, we're gonna multiply by -1 to both sides. So A13 plus A12 equal 1. That means you only can choose either way to go to Virginia Beach. So what about the node 2? This is about node 1. And what about node 2? There is only one inflow traffic from node 1, 2. So A12, and then we have two outflow from 2 to 3 and 2 to 4. So 2 to 3 minus 2 to 4 should be equal 0, because you have demand 0 for all other nodes in this case. What about node 3? We have two inflows from 1 to 3 and from 2 to 3. And then we also have two outflows, -3,5 minus A36 equals 0. So you're gonna do the same way to define the constraint for all other nodes. So, but let's take a look at node 11's constraints. There are two inflows, A911 plus A1011 minus, there is no outflow, so 0 should be equal to +1. And the last set of constraints, all decision variables should be greater than or equal to 0. So we used quickest route. We try to find the quickest route by minimizing total travel time from Birmingham, Alabama to Virginia Beach in Virginia through many different roads. So final solution you can find from the Excel file. I'm going to upload. After this class, you'll be able to find Excel files, Excel solutions.